Okay, moving on. Give an example of a function which would have a left arm up and a right arm down. Okay. All right. This didn't translate well when I downloaded it, so I'm not really sure what this says. Let me see if I can find it in the original. Oh, okay. So that had the arrow notation, which didn't translate well when I put it into my note-taking application. But here's the idea. Left arm up, right arm down. You can do whatever in between, but this is the overall kind of function we want. So any function that is odd, that has a lead coefficient that's negative, would be a perfectly fine answer for this. For example, f of x is equal to negative 5x cubed. That would be an example of a function which would have a left arm up, right arm down. Why? It's odd, so the arms go in opposite directions, and because this coefficient, the lead coefficient, is negative, we know the function falls. But that answer is not unique. There are many, many answers that are fine. Just make sure that your answer has an odd degree and the leading coefficient is negative. Okay, moving on to section 3.4. Given this function here, find the zeros and state the multiplicity of each. So remember, zeros is another word for roots, all right? And so to find the roots of a polynomial that's in factored form, super easy. You just set each factor equal to 0. So one root is negative 5. And notice that that degree is 3. So that's a root of multiplicity 3. For the next root, this one here, the next root would be negative 2. And that has a multiplicity of 2 because of the power here. And finally, the third root is x is equal to 1. And that simply has a multiplicity of 1. Finding the zeros. Describe the behavior of the graph at f of x at each of the zeros. When you have an odd multiplicity that's greater than 1, the graph is going to flatten out and then crosses the x-axis. So just as a reminder, what would happen at negative 5, so out here at negative 5, now we could see if it was positive or negative, so that's more detail than we were asked to go into in the problem, but it would do something like this, flatten out and then cross. Or it might be going downward, we don't know. We'd have to do a little more work to determine which direction, but all we were asked is what it does at the root, and what we know is because it's a degree that's odd and higher than 1, it's going to flatten out. Okay, what's going to happen at this root? At this root, it's going to bounce. So at negative 2, and again, I would have to do a little more work to know that if it's positive or negative there, but it's either going to do this or it's going to come from the other direction, bounce up and go down. But it's going to bounce in any event. And then finally, if it has a multiplicity of 1, a multiplicity of 1 at 1 simply means it's going to cross the axis. And again, we don't know what direction it's crossing in, whether it's rising or falling. We could do a little more work to figure that out, but we were just asked what it's going to do at that particular point, and at that particular point, we know it's going to cross over. Okay. Find a polynomial function that fits this graph and explain how you found the function. So in this function, we can clearly see what the roots are. So the roots are negative 2 and positive 1. So since we know that those are the roots, we can start building the function. F of x is going to have x plus 2 as a factor and x minus 1 as a factor. Now, one thing to notice is that at these roots, the function bounces. that means that each of these factors has a multiplicity that's even. Whether it's 2, whether it's 4, we don't really know, but let's just use 2 as an example. Okay? Now, there could be a constant that's multiplied by it, so that's what we're going to find next. So to find what a could be, we pick any point on the function. So let's pick this one here. The y-intercept is always a nice, easy one to use. That's the point 0, 4. So that means when x is 0, y is 4, and that's going to allow us to solve for a. So putting that into our function, 4 is equal to a times, remember x is 0, so 0 plus 2 is 2, so 2 squared. X is 0, so 0 minus 1 is negative 1 squared. So let's go ahead and simplify this. So this would be 4 times 1, that's 4. So 4a, so a could be 1. So a function that could have this for a graph would simply be f of x is equal to 1 times x plus 2 squared times x minus 1 squared. Using technology to find x-intercepts, that's using your calculator. I'll make you a separate video from my computer screen where I remind you how to do that on a TI calculator. And finally, finding a polynomial of degree 3 that has roots of 2, 1, and 3, and a y-intercept at 0, negative 4. Problem number 7 is exactly like problem number 5, except in problem number 7 I gave you a description instead of a graph. So if 2 is a root, so let's start constructing our polynomial. If negative 2 is a root, then we know x plus 2 is a factor. If 1 is a root, then x minus 1 is a factor. If 3 is a root, then x minus 3 is a factor. It didn't say anything about having higher multiplicities, so we're just going to leave them at multiplicity 1. And there could be a constant a being multiplied by those factors. To find out what a could be, we plug this in for x and we plug this in for y, or in other words, f of x. All right, so here we go. Negative 4 is equal to a times 2 times negative 1 times negative 3. In other words, negative 4 is equal to, if we multiply all those together, we get 6a. So negative 4, 6 is equal to a. And if you wanted, you could reduce that to negative 2/3. So a function that has the roots described, that passes through 0, negative 4, would be negative 2/3, x minus 2, x minus 1, x minus 3, and this is actually a plus. All right, so I'm going to go back and I'll make another video for number 6, and then that will finish this week's Check for Understanding.
Hello.